Today we are going to discuss on the commutative property of operators. The last class we already saw what is meant by operators and the algebra of operators, addition, subtraction, multiplication, all these properties. Okay, and today we are dealing with one of the important properties of some operators, and that is called the commutative property. Commutative property. Commutative. Commutative property. Commutative property. Okay. So let us consider two operators, a cap and b cap, and we let these two operators to operate over a function f of x. Okay, so a cap and b cap has a freedom to operate over the function f of x. Okay, and we are doing this operation in two ways. One is a cap b cap f of x. It means that b cap is operated over f of x first, then it is operated by a cap. Okay, I can now reverse the order of operation, that is b cap a cap f of x. Means over the function f of x, a cap is operated first and then it is followed by b cap. Okay, in these two ways I can let these two operators to operate over a function f of x. And when we are doing this, we will get another function. The first case, we will get a gx, for example, let's say gx. And in the second case, let us get a function h of x, okay? And it is not necessary that g of x is equal to h of x. Sometimes g of h may be equal to h of x, and sometimes g of x may not be equal to h of x. Okay, so if g of x is equal to h of x, it means that if this is the case, g of x is equal to h of x, in that case, a cap b cap f of x is equal to b cap a cap f of x. What does it mean? Means the sequence of operation doesn't matter in this case. Okay, usually you get a result. The operation of two operators over a function largely depends on the sequence of operation. But if this sequence of operation doesn't matter, like a cap b cap f of x and b cap a cap f of x gives the same result, in that case you can say that a cap and b cap are commuting. Okay, so what is meant by commuting operator? Okay, um, commuting operator means that when if two operators are such that the result of their successive applications is same, the result of their successive application is same, irrespective of the order of operation, then the two operators are said to be commutative. So A and B are commutative operators. Commutative operators. So let us say once again what is commutative operator. If two operators A cap and B cap are such that the result of their successive application is same, irrespective of the order of application, then the two operators A cap and B cap are said to be commutative. Okay, so let us check some examples. And let us take a cap. A cap is equal to d by dx. Cap is equal to A cap is equal to d by dx, and b cap is equal to 3x square, and the function f of x is sin x. Okay, so let us check whether a cap and b cap are commutative. Okay, so first let us do this step, the first step, that is a cap b cap f of x. Okay, a cap b cap f of x, this one. a cap b cap f of x, and we will check what's the result, and then we will do b cap a cap f of x, and then we will check the result. If these two results are same, that is gx is equal to h of x, then we can say that a cap and b cap are commutative. So let's check a cap b cap f of x. A cap b cap f of x is equal to a cap is d by dx and b cap is 3x square f of x is sin x, okay, sin x. So what is the first operation? Means this right operator is operating first over the function. Means 3x square is a multiplication operator, so 3x square will multiply with the sin x. So the result is 3x square itself. Okay. So now we have to operate with the second operator, that is d by dx. So what is the derivative of this function d by dx of 3x square sin x? So that is equal to, how can we do this? This is the product of two functions, 3x square and sin x. We can keep 3 as a constant, then 3 of d by dx of x square sin x. Okay, so we can write it like 3 into d by dx of x square sin x, that is first function x square, the derivative of the second, that is cos x, plus second function, that is sin x, into derivative of the first, that is equal to 2x. Okay, so that is equal to 3x square cos x, 3x square cos x plus 3 into 2, that is 6x sin x, 6x sin x, right? 6x sin x. Okay, so that is equal to 3x square cos x plus 6x sin x. That is our first result when we do a cap b cap f of x. Now we are going to do b cap a cap f of x. So that is equal to b cap in this case is 3x square, and a cap is d by dx. So 3x square d by dx of f of x is sin x. Okay, so that is a pretty easy result. So that is equal to 3x square into, we have to operate sin x with the right operator, that is d by dx. So d by dx of sin x is equal to cos x. Okay, so the result is 3x square cos x. This is the result. So in both cases, when we are doing a cap b cap f of x and b cap a cap f of x, in both cases we have different results. The first case, the result is 3x square cos x plus 6x sin x, and in the second case the result is 3x square cos x alone, right? So in this case, the two operators are non-commutative. If it should be commutative, the results will be same. Since the results are not same in both cases, means the result depends upon the sequence of operation, right? So since the result depends upon the sequence of operation, they are non-commutative. Okay. In the case of commutative operators, the sequence of operation doesn't matter, but here the sequence of operation matters, so they are non-commutative operators. Which are the non-commutative operators? 3x square and d by dx are non-commutative operators. Now we can check another example, and that is, let us consider a cap is equal to d by dx, and b cap is equal to d square by dx square, So these are the two operators, and the function f of x. In this case also it is sin x. Okay, and now we can perform a cap b cap f of x. A cap b cap f of x, that is equal to d by dx of d square by dx square of sin x. Okay, so we have to do this first, means the right operator should operate first, Right operator is d square by dx square. It should operate over sin x. What is d square by dx square of sin x? That is the second derivative of sin x, but that is equal to minus sin x. Okay, so we can write it like that is d by dx of minus sin x, minus sin x. Now this function should be operated with the left operator, that is d by dx of minus sin x, that is equal to minus cos ax. Okay, minus cos x. And now we can check b cap a cap f of x, b cap a cap f of x. Okay, now b cap a cap f of x is b cap is d square by dx square and a cap is d by dx of f of x. F of x is sin x. Okay, so this must operate first, d by dx of sin x. So we can write d square by dx square of d by dx of sin x, that is equal to cos x, right? So now we have to operate with the second operator, that is the left operator, that is d square by dx square, and the result is d square by dx square of cos x. What is d square by dx square of cos x? That is also equal to minus cos x, minus cos x. You know how to do this? Because when we are doing d square by dx square, we have to first take the first derivative, that is the first derivative of cos x is equal to minus sin x, and then we are taking the second, again one more derivative of minus sin x, that is equal to minus cos x. Okay, so in this case also the result is minus cos x, and here also the result is minus cos x. Okay, so in both cases we have the same result. It means that a cap b cap f of x is equal to b cap a cap f of x. It means that a cap and b cap are commutative. Okay, so in this case d by dx and d square by dx square are commutative operators. They are commutative operators. Okay, now you understood what is meant by commutative operators and non-commutative operators. If the sequence of operation doesn't matter, they are commutative. If the sequence of operation does matters, then they are non-commutative. Okay, now there is some significance to this this kind of things in quantum mechanics, and that you will learn later on when we are learning the second postulate of the quantum mechanics. But I can just mention why it is important in quantum mechanics. The significance of the commutating operators is that if two operators are commutative, okay, the physical quantities corresponding to these operators, okay, they can be simultaneously and precisely determined. Okay, um, I will explain that in a little detail, but I will come to more detail when we are learning the second postulate of the quantum mechanics. In quantum mechanics, actually, corresponding to every physical quantity that we are talking about means, for example, angular momentum or linear momentum, kinetic energy, or total energy, whatever it is, whatever measurable quantities that we are talking about, corresponding to every measurable physical quantity, there is an operator. Okay, for example, momentum is an operator. Momentum is a measurable physical quantity. Corresponding to momentum, there is an operator. For example, we can write it as px cap. Okay, and position, corresponding to position, there is an operator. Let us write it as x cap. Okay, so if you are seeing that two operators are commuting to each other, the physical quantities corresponding to those operators can be precisely and simultaneously measured. So what will be the result in these cases? Here it is momentum operator and the position operator. And if do you think that these two operators will commute? Or if these two operators will commute, it means that if px cap x cap is equal to x cap px cap, in that case we can say that it is commuting. If they are commuting, it means that the physical quantities corresponding to these operators can be simultaneously and precisely measured. Means physical quantities are momentum and position. Momentum and position. Okay. If they are commuting, the momentum and position of a quantum mechanical system can be easily or precisely and simultaneously measured. But we know from the uncertainty principle that that is not possible. Position and momentum cannot be precisely and simultaneously measured. So this is not a possibility, right? So px cap x cap will not be equal to x cap or px cap. Okay. So they will be non-commuting operators. So if two operators are commuting, the physical quantities corresponding to those operators can be simultaneously and precisely determined. If they are non-commutative, the physical quantities corresponding to those operators cannot be determined simultaneously and precisely. That is the significance of these commuting operators in quantum mechanics. Okay. Now we are going to wind up this lecture just by introducing another terminology, that is commuter operator. Okay, commuter operator. We are going to introduce another operator, commutator operator. So commutator operator. Commutator operator. So what is commutator operator? You know the two operators, a cap and b cap, a cap and b cap, and you think that a cap and b cap are non-commutative operators. It means that a cap b cap is not equal to b cap a cap, b cap a cap. In that case, if you are expressing a cap b cap, a cap b cap minus b cap a cap, okay, that will be a non-zero quantity, right? Because a cap b cap is not equal to b cap a cap. Therefore, a cap b cap minus b cap a cap will be a non-zero quantity. Okay, so non-zero means the operation of this combination will not let the function to be zero. Okay, so a cap b cap minus b cap a cap, this is an operator. Okay, this operator, we can put it that in the square bracket. This operator is called a commutator operator. Commutator operator. Commutator operator. Okay, commutator operator. So we can check two operators. For example, the momentum operator and position operator. Okay, because we already know that they are non-commuting operator from the uncertainty principle. So position operator, the momentum operator, px cap. This is the linear momentum operator in the x direction. Okay, so this is equal to h divided by 2 pi I d by dx. You may be wondering how I got the expression for this px cap. Don't worry, we are going to learn this. We will get this expression later on. Okay, we will learn this in detail. So at this moment, you just understand that the momentum operator is h divided by 2 pi I d by dx, and the momentum operator is x cap. Okay, that is just x. It means it is a multiplication operator. Okay, so now I am going to take a function, that function be an imaginary function. Imaginary, just imaginary, just not imaginary, we cannot say imaginary, hypothetical function f of x, whatever it may be. Okay, so it can be any function. Let us take a hypothetical function f of x, and let us operate f of x with both this x cap and px cap. And first of all, let me operate this with px cap x cap in this order. with f of x. Okay, so I'm going to do this operation. Then I will get px cap is equal to h divided by 2 pi I d by dx, and then x cap is nothing but x. Okay, d by dx, and then x f of x, f of x. So what is the order of operation? The first operator is x, so that will operate over f of x f of x. And after that it will be operated with the second operator, that is h by 2 pi I d by dx. Here h by 2 pi I is a constant, so we have to operate this function x f of x with a d by dx. So we can get h divided by 2 pi I d by dx of x f of x. Again, this is a product of two functions. X and f of x are two functions of x, and then we can take the first derivative of the product of two functions. How can we get it? That is, first function x into derivative of the second d by dx of f of x, that is equal to f dash x, okay, plus second function, and that is f of x into derivative of the first derivative x is equal to 1. Okay, so we get h divided by 2 pi I x f of x, x f of f dash x, f dash x represents the first derivative of f of x. Okay, so h by 2 pi I x f dash x plus h 2 pi I h 2 pi I f of x. Okay, that's the result. Now we are going to calculate what is the result of x cap p x cap f of x, the reverse order. Here it is px cap x cap f of x, and now it is x cap px cap f of x. So that is equal to x into px cap. Px cap is h2 pi I, h by 2 pi I d by dx of f of x. F of x is f of x. F is a hypothetical function that we are using now. So what is the result? First we have to operate f of x with a d by dx. H by 2 pi I is a constant. You can keep it there like that. So we get x into h divided by 2 pi I d by dx of f of x. What is d by dx of f of x? F dash x, right? So we have to we have obtained another function h by 2 pi I f dash x, and that is to be operated with the second function, that is x. That is a multiplication operator. So what we get? H by 2 pi I. Multiplication operator means you just multiply this with the function side. So h by 2 pi I x f dash x, that is the result, right? H by 2 pi I x f dash x. Now you compare the two results. Here in the above case, where we use the order p x cap x cap, we got the result h by 2 pi I x f dash x plus h by 2 pi I f of x. Here we got h by 2 pi I x f dash x, right? So this term h by 2 pi I x f dash x and h by 2 pi I x f dash x is same in both cases. But there is a difference. In the first case, we have an additional term, that is h divided by 2 pi I f of x. So that is an additional term. So what is the difference between these two? H divided by 2 pi I f of x. So we can write it like px cap x cap f of x minus px minus x x cap x cap px cap f of x is equal to what is that h by 2 pi I f of x. This is the difference, right? So h divided by 2 pi I f of x, h divided by 2 pi I f of x. That is the difference. Or you can write it like px cap x cap minus x cap px cap, okay, f of x is equal to h by 2 pi I f of x. Okay, so we can write this one, what is here inside the bracket. Px cap x cap minus x cap px cap is equal to h by 2 pi I, because this operate on f of x is equal to h by 2 pi I operates on f of x. We can interpret it like that. So this function, this operator, what is inside the bracket, means px cap px cap x cap minus x cap px cap is equal to h divided by 2 pi I. That is a non-zero value, right? So this one, px cap x cap minus x cap px cap, that is the commutator, that is the commutator operator of these two operators. So this is the commutator operator, commutator operator. Okay, so the commutator operator is possible only when the operators that we are considering are non-commutative, right? Means there should be a difference. Then only the commutator operator will be evolved. Okay, so if there is a commutator operator existing for two operators, it means that these two operators, they do not commute, and it is not possible to determine the precise values of the physical quantities corresponding to those operators. That is the meaning. Let me say it once again. If a commutator operator exists, it means that the operator corresponding to those commutator operator, they are non-commutative, and therefore it is not possible to determine the precise values of physical quantities corresponding to those operators. Here, the position operator and the momentum operator, they have a commutator operator. It means that the position and the momentum cannot be determined simultaneously and precisely. That is the quantum mechanical implication or quantum mechanical significance of studying this operator property. Okay, I hope you understood about the commutative property of the operators. And if you have any doubt, please don't hesitate to ask me. Thank you for watching, and stay tuned.